So it's already late and maybe everybody's tired, but I suggest that we have a small moment of recapitulating what we have done, questions, trying to answer the questions you have, whatever. So I'm here. So does someone want to show his or her work? Do you want me to show how difficult it is to do lean myself when I do it myself? Do you want? Yeah.
Well, I've got the solution to one of the number theory exercises that took quite a lot of lines, and I wondered if there was a short.
Do you want to show it?
Sure.
So then you can come and can switch off my computer and switch on yours. So, sorry, excuse me, I will do that. To use.
Mine's a PC.
So you use directly the HDMI.
Yep.
But you will lose the, you don't need the adapter.
No.
It's okay. You don't need the pointer.
Oh,
you won't have a pointer. Okay. Yeah, you will have space, but
yeah.
Of course. It's easier this way.
So.
Okay.
So I'd like to look at exercise.
Ah, sorry. Put something.
All right. So I'd like to look at exercise 8. So that says, suppose that we have a solution to a linear Diophantine equation, ax plus by equals c, and show that you can get all x and all y by doing a certain parametrization where you take x naught and y naught and you add integer multiples of b over d and a over d, where d is the GCD. Did anyone else attempt this problem? No, okay. So, oh yeah. So your solution's very long. Okay, so I'll show you how we did it. So let's see. The first thing is that it refers to the a divided by d, and that's an integer division. And you cannot use anything like the ring tactic on integer division because that's a floor division. And so it's not mathematically well behaved. So the first thing that we want to do is we want to Qify this. And first we want to show that if you do the division in Z, that gives you the same answer as doing the division in Q. So this notation forces A to be Q on this side, Z on that side, and then the integer is promoted to a Q for the comparison here. And the nice thing is that if you just type apply with question mark, you find that Lean does have a method for doing that if you can show divisibility of the corresponding integers. So I do that, and then I use the way that D is defined to solve that. And I do the same thing with B. Questions so far? And now we split into the two directions. So I decided to swap the goals because the easy direction is to show that if there's a T with this property, then this equation holds. So we do that. And then we have these two hypotheses. And at this point, it should be a linear relation. So we Qify. And we Qify everything that should be relevant. So this equation should be a linear combination of this one, and this one, but with certain coefficients, some of which may be rational. So we do that. And then we get this, and you see it's got the promotion of the integer division A over D. So we got to rewrite using the lemmas that we already have. And then we plug the equations into each other And so we get a complicated expression, but that has fewer variables. And therefore, we figure that it should be true by field simp to get rid of the denominators, and then ring to solve the problem with the multiplications. Now, going the other way, we have the assumption that we have two of these both equal to the same C. And okay, C does not appear in the goal. So we think, okay, we should set these equal to each other and simplify. And that's what I've done here. And I also wanted to divide through by D to get closer to my goal. So we prove this result by first Qifying the relevant statements and then changing the integer divisions to rational divisions, and then field simp. And then indeed, it is the difference of the two equations, linear combination. And then our goal is to prove there exists a T. And there's this awkward fact that to give a formula for what T is, there is no one formula that works in all cases. Because you'd like to say T is equal to x minus x naught divided by b times d, but what if b is 0? And so we have to divide into two cases, and we use the not equal to or equal to statement that says that one of these two is true, and that's what we're going to do the inductive R cases tactic on. So we first assume that it's not 0. In the interest of time, I won't go into the case where it is 0. It's very similar. So what we do is, so we want to show that there exists such a T, and we want to get it by dividing x minus x naught by b over d. So first we should show that one divides the other. And to do that, well, how do we show that b over d divides x minus x naught? Here, all of a sudden, there's actually some number theory involved because we have that it divides this product. And if we know that it's coprime to a over d, then we can apply Euclid's lemma to show it divides the other factor. And so that's what we do. We apply this, which is Euclid's lemma, but it has a name where you might actually be able to find it. By the way, if you search for Euclid's lemma, your first 10 hits have to do with Euclidean geometry. But if you type in Euclid's lemma GCD, you find it. And then exact, so let's see, what's the goal here? So we got to fill in this meta variable. So we want to know why does it divide. The divisibility is the proof with two things. One is how many times does it divide, and that's y naught minus y. And the second is why does that product match, and that's EQD. Yep. And then the remaining goal is the coprimality. And that was more or less the previous exercise, which also is known as int.gcd div gcd div gcd. And then you get a positivity where you have to use the hypothesis that the GCD is non-zero, which basically says they're not both 0. So you use that. And you ask exact question mark, and it uses all these funny things to show that if the GCD is not 0, then it's let's see, if it's anyway, you convert naturals to integers and also positive to non-zero. All right, and then once we have that divisibility, then that divisibility gives us our T, and we can finally use T and prove the stuff that we want. And so now again, we think it's a statement that's true over Q. And so we do that. And we use constructor because we're trying to prove an and. And of the two statements in the and, the first one is the exact same thing as our HT, just with some terms moved over, so we use linear combination. And then for the second one, we first get rid of the integer divisions, and then it's a little tricky. It's basically a linear combination of 3 of these equations, but with denominators. And so we can first rewrite to move terms to the other sides, and then we multiply through by b over d, and get rid of the functions by dsymp. And then at this point, we can substitute in the one and the other. And we use this apply fun. We need an injectivity. And we know that multiplication by a non-zero thing is injective. And so we use the proof of that. And yep. And so the rest of it is when b is 0. And then there are a few cases, basically, when you simplify that, you get that the GCD is the absolute value of A. And so then you have to further break into cases based on whether A is positive or negative, and it does work out.
My proof is not shorter, but I stayed on the integers because I didn't know about QE5 last week.
Okay.
So the first move I made is showing that A divided by D, integer division, multiplied by D is A, and getting a new name for A prime is A mod D, and writing everything in terms of A prime and multiplying. Basically, it's more or less. Cool. Thank you. Sorry.
Excuse me. Oh, I'm not here. Oh, thank you. Yeah.
So do you wait? Yeah. Sure. One minute. Give you the microphone.
I think, the example brings to mind, like we have, maybe that's the longest proof that we've seen with a lot of code, like more than you can kind of take in an eyeful. And in the world of software engineering, like, it's a matter of taste, but a lot of people like to have small functions, right? Because you can have a small unit, you test that unit, it's good for the human, you can pretty clearly, you don't have to have too much context in your mind to understand what's happening. And I guess my question is for the people that have written more lean code and been exposed to like bigger lean code bases, to what extent the same phenomenon is there, or can we even expect it there in the context of substantial proof?
Okay.
Because it's also different, because the practice is different because we have this interactive assistant that is working with us, and that's different than when you're just writing code outside of a prover.
So what I can do to try to answer your question is to open one random file in Mathlib. But it won't be a random. I mean, it will random against the law of probabilities of which file is of interest to you. So what kind of theorems would you like to have a look at? You see, Mathlib does a lot of stuff, which is there. So here it's, we'll have a look otherwise. Where is index? Maybe? No. Where is the documentation that says what is currently covered theories? So is there a theorem you would like to have a look at? Maybe.
Can we see scheme?
What?
Scheme?
Scheme?
Yes.
But are you fluent on schemes? Probably not. I'd like to see schemes, but Chinese Romanians. Okay. let's look at it. So let's try to find it first. So you see, I lost. Okay, I need to go to Mathlib for docs, and let's try. But I fear that if I type remainder or Chinese remainder, oh yeah, not Chinese remainder. Here it is. So natural number less, maybe I should is bigger. So where is it? There was another one at the top. Let's type it again. Okay, now I need to do that. So I said that if n and m are coprime, two integers a, b, it gives you an element in k. Okay, it's really a function that takes two integers, two natural numbers, a and b, and give you a natural number k, which belongs to the set, actually to the type of natural numbers which are congruent to a mod n and to k mod m. Okay. So maybe we'll have a look at the source. So it will probably be easier if I open a file, close my stuff, and go to my own. So do you remember the file Mathlib data nat? Okay, data nat mod ec, and then I will maybe make a bigger font. Yeah. Oh, but I can also make better. Just need to ask. So here's one, and here's the other one. So if we have a look at the proof, okay, Chinese remainder, which is the one we're interested in, it just calls another one. So we'll have a look at the first one. Here's the function. So you see, it takes one hypothesis that A is congruent to B modulo the GCD and N and M, and it constructs an integer k. And so one has to think about what it means. Oh, okay, because it's a more general stuff. I mean, the Chinese remainder theorem that we used to is for M and M which are coprime. Here they have not necessarily coprime. There is a GCD and M here, which might be 4. And then the condition is that A and B have to be congruent mod 4 so that you can solve it. So in fact, this Chinese remainder theorem is a more general version. Okay. So now let's go to proof. So its first case is n is 0, what to do something. So you can see a syntax. So it's really a function. It's a programming language. So you can say that something is if then else. And so the function Chinese remainder theorem applied to the argument h. As for value, this stuff, oh, sorry. This stuff, a blah, blah, blah. No, what's happening? So it's this stuff. Oh my God. I'm totally confused with my editor now. Okay, so well, at least that stuff. That stuff when n is 0, and when n is non-zero, it's the subcase, what happens if m is 0, and then the final case, which is a proof, which is quite not so short. So, and what? A derivative will be just a definition. Or one has to find the mean value theorem first. So how is it called? So then we can go to Google, for example, things like that. Type no, nothing like that. Well, it's not so good. So then what would I do? But I don't know how to do that. Except that I can do something like that. You see, I'm not a very, so I can do grep mean minus I, mean value, Mathlib, and blah. Wow. So we have something in Mathlib analysis calculus F deriv. So here. Oh, it's even better. Okay. So in this file, we prove Cauchy's and Lagrange mean value theorems and deduce some corollaries. So you have a statement, explanations. Lagrange means that there is something with a slope, and at the end, and probably there are more general theorems, but okay. So here at least it's worth thinking. So you show that it shows that in the documentation you have some the important functions which are defined in the file, which are explained at the beginning, and this reflects in the. So I take this stuff, exist ratio something, and I copy it over there because I did not copy correctly. So if you go there, you here, and here you have this command, and at the beginning you have the same file, the same beginning of the file, but nicely typeset. So here that. So we can go there, and here you have the statement. And let's go to the code. Here is it. So you see it's very close, it's very short because it says that there is something. First, there is a function which is defined. So it's written like let hx. So h was not defined. So it really means that it's a function of a variable x, and which is gb minus ga times fx minus fb minus fa times gx. And then it is proved that this function takes the same value at a and at b. And then here it is. And so the proof is basically just unfold H and do some, and then apply ring. Okay. Now there is a computation, yet another definition, so that the derivative H prime is not the derivative of H. It's just a notation H prime. And then there is a theorem, HHH prime, which says that for every X inside, so IOO is the interval from A to B, and it's open on both sides. So there is IOO, IOC, ICO, and ICC. And there is also IOI for infinite in this direction, and IIO, and IIC, and ICI, and maybe III. which means, okay. And so the statement is that the derivative, so has derivative at h prime x really means that the function h has for derivative at x the value h prime x. And so, well, we can't see it. So, so that means that it's something for all x in something, some property. So this stuff is a function from real numbers to prop to prop. It takes, and so x will be here. Maybe we can see it. I don't understand why I don't see. I can't see the stuff. It's here and the way. Maybe because there is no bar, yeah. But I can't modify the file. Oh, yes, maybe I. Okay. And so now, so you see, we don't have this nice map to symbol, but equals superior, which was the way it was typed before. Now we're used to type this, but it's the same. But, okay, and now how would we prove that? Because there is another lemma, probably HFF prime, that says here on right that the function f prime, which exists here, as if f prime x is the derivative of f at x. Here is this lemma. So there is a lemma that says that if you take if you have as deriv at and you apply it to a sum, that you get as deriv at for both statements. So now you have the derivative. It's the same for the function h is continuous on the closed interval ab, which is what is meant here. And now from that, there is this fancy lemma exists as deriv at equals 0. Maybe we should go to it. That apparently takes many arguments. The HAB is that A has to be strictly smaller than B. It's over there. HHC means blah, 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 that there's continuity on the closed interval. HI, that both values are equal. You see it here. HHH prime, the derivative property. And then, in fact, we get from this lemma that there exists an element C in the middle, that a real number that belongs to the open interval, and HC will be the fact that the derivative is 0. And in fact, what we get is that there exists C. We have to prove that there exists C in the open interval, IAB, with some property. And this is essentially what has to be proved. So this is Rolle's theorem, exists as 0. So maybe we can go to it, and it says that it is Rolle's theorem derivative. And again, the proof is very short, but the proof is nice. So you see, you really recognize the classical proof. So we want to prove that there is some derivative which is 0, and say, okay, we have this statement exist is local x IO, that apparently will mean that there is a local extremum in the open interval. And you'll take something where you'll take this point C, which belongs to the open interval, where AC is HC will say that it's a local extremum. And then we'll get for an answer, we'll take this point C, it belongs to the interval, and we just have to apply the theorem that at a local extremum, the derivative is 0. And probably, okay. Yeah, okay, probably, which is nice. Now it's fun is to look at the next one. So, so now we apply the theorem that the derivative is 0. It's yet another theorem of Fermat, that if you have a local extremum, that derivative is 0. And you see it's proved by if it's a local minimum, is 0. And if it's a local maximum, is 0 again. The next lemma is very fun, because if you look at the statement, it says that if you have a continuous function on the closed interval AB, which takes the same value at A and B, then there exists a point in the open interval where the derivative is 0. And if you say that to first-year university students, or if you say that as a first-year university student, you get a bad mark, because you're supposed to state the assumption that the function has a derivative. But for Lin, the function deriv f is defined by if the function has a derivative at x, then give the derivative, otherwise put 0. So you don't need to assume that it is differentiable everywhere, but okay. So you have Froll theorem. And then we could try to go to back to the proof. Okay. And the proof, and they redo the proof, in fact, you see, that says that there is a local extremum, and there is, again, the statement in terms of the derivative. So, okay, we have to look at a local minimum, there is derivative, and here you see the proof. So if you have a local minimum at a point A, then the derivative is 0, and you have a distinction. If the function is differentiable, then you apply the Sayers theorem. And if it's not, then there is a statement that says that by definition, the derivative is 0 otherwise. What other theorem could we have a look at? No? Let's you want to do it? Okay, so yeah. So I have to guess what it is. Will it be an algebra or complex? Complex is closed. You see, that should do it. Okay, so let's try to go there. Mathlib analysis, complex polynomial basis. Okay, so the file is fully devoted to that. So fundamental theorem of algebra, which, as it should, is in the analysis section of Mathlib. Sorry?
What is formalization?
Oh, Bono. Aha. Well, we'll see. So first we are looking at the theorem. Okay, so the proof you see is a little bit short. I mean, it's by contradiction. You want to show that if we have a polynomial of strictly positive degree, then it has a root. So assume it does not. Then we'll apply Liouville. Okay. So we need to prove that there is a point where the inverse is 0. And whoa. So this is the way some people write proofs. So it's really a composition of 20 or maybe 20, at least 5 or 6 lemmas. And you can really say the F composed with G, composed with H, composed with lemma 1, composed with lemma 2, and so on. And you write it in this way. So it's hard to know, to guess what it means. And also there is this very fancy notation, inferior pipe, which means a parenthesis from there to the best point, but the further you can. So this means probably from here to the end.
Which out of all of those different bits? Is it that one?
Q of tends to.
Is that one?
So maybe we can try to just, so what this tends to, let's say that the norm tends to norm at top, filter tends to inv co-bounded. Oh my God.
Yeah, I think it is apply equal out the first one.
The corollary, okay. It says that,
Oh,
yeah, because there is Bornology co-bounded. So at least the statement is interesting because you see, well, let's go to it. It shows how Mathlib is built. So you have some E. So we have some E, which is a normed adcom group. So it's an additive group, commutative additive group, and with a norm. And it's also a norm space over the complex numbers. And we have another F, same, which is also a norm space. E is supposed to be non-zero. And a function F from E to F, which is supposed to be complex differentiable in the complex sense. And an element C in F, so which will be some value, and a point X in, okay, and the point S, F, oh, sorry, and the point F is, the point X is anything. And we will prove that F of X is something. And why is it C? Because there is this statement that F tends to C at infinity, because co-compact E is a filter of complements of compact subsets. So this statement, HB, means F tends to C at infinity, and then F is constant of value C. So the slight difference between this statement and the one in the book by Rudin, the second one, is that E, the function does not go from C to C, but from any complex vector space to any other complex vector space. So that there is a derivative. And the derivative differentiability probably means in any direction or something like that. Well, should Frechet different, it's Frechet probably, okay. Okay, and then, well, there is a proof like that. Okay, so now if we go back to the statement, it means that we will apply the theorem. We will know to show that the function f will apply the function to f minus 1. So we need to know that f minus 1 is differentiable. So because f is differentiable, there is a statement that says that f minus 1 is differentiable, and it's called differentiable.inv. So now we can apply f dot differentiable. We just put a dot inv, and it says that f minus 1 is differentiable, probably. And so that we need that it holds that the hf prime, it's only differentiable at points which are not roots. So maybe we should do that like this. So we can just try to unfold this. I will ruin the file, but so you see H1 is that says that the function is differentiable. H2, it says that if I give myself a point at which the function is non-zero, then the inverse is differentiable. So if I put HF prime as a hypothesis, I get that the inverse is differentiable because it was understood. Maybe this doesn't work. So then I could try to, let's try H2 dot apply ec of tends to co-compact Z. Doesn't work. Maybe. Oh.
C colon equals 0.
Sorry.
C colon equals 0. It can figure out what the C is supposed to be, but your C is supposed to be 0.
I'm not yet. Okay, so now we have H3 that say that if we can prove that f minus 1, the inverse of f, tends to 0 at infinity, then we'll prove that inverse of f will be 0. And since we need to prove that the inverse of f is 0, then we can apply H3. And now we have to prove that inverse of f goes to 0 at infinity. So now it's a second part of the proof. So let's try metric. What does metric dot co-bounded equal co-compact? And probably AC made a mistake. Yep. So that's well, it's a filter. Okay. So that's just a filter of co-compact subset, which is bizarre stuff. No, it's an equality. It says that the field of co-bounded functions in C is the same of co-compact function. Okay, the same filter. So the complements of compact subset is exactly the set of complements of filter of. So that is for H4, and then we can look at the stuff. So it's really fun because so we try to take the last sentence, but I will copy it because it's too complicated. Copy this up to here. Okay, does it work? Yep. So I have something that says that filter tends to the inverse. So in composed with fun x to eval x f is really the inverse of the 1 over f. That it tends to 0 at infinity. Okay, and this is because, well, this is again a composition of a lot of stuff. Because probably there is a theorem that a polynomial tends to infinity at infinity, so the inverse of a polynomial. Yeah, and why is the assumption that the degree is positive? Boom, boom, boom.
It's right there to the right.
Yeah, here there is HF. So, and probably tends to norm at top. There is an assumption, yeah, there is H that 0 is strictly smaller than the degree of B. Okay, so now we have H5, and from H5, there is this fancy triangle. So probably, yeah. So what is written is that and what it means is that we are rewriting probably, we rewrite the equality co-bounded C equal filter co-compact C inside the stuff that we just had. And the arrow is the same of rewrite, so it's really a substitution. And then, is it okay? And then we have something, we have this, we have that 1 over f tends to 0 at infinity. And now we will conclude that f is 0. No, I need to, I am missing something. Now I need to apply, I should say H6. And now I need to apply H3. You see, the H3 is really an implication. If that 1 over f tends to 0 at infinity, then the function 1 over f is constant everywhere. Sorry. here, this stuff. And here, H6 is really the hypothesis of H3. So I could define H7, which is H3, H6. And that really says that 1 over F is 0. And now we need to prove that F is constant equal to 0, and which is the end. And and now there is something that the inverse is injective. The function inverse is injective. So this is the inverse function of Mathlib. So it sends a complex number to its inverse if the number is non-zero, and it sends 0 to 0. That's even bijective. So the function, if the function here, which is injective, it's really saying that the function from the complex number to itself that sends z to 1 over z if z is non-zero and 0 to 0 is injective. It is even bijective. So I think it's doing that. But so maybe we can try to say H8 and to have a look, no, H8, to have a look at what's over there. Let's try this. Okay, it didn't work because, no, it's because we need the full stuff. What did I do? That doesn't work. Probably it's not clear where the problem is here.
Maybe it means the type annotation.
Yeah.
F equals C of 0.
So it sounds like it's proving analytic function, entire function goes to infinity.
Yeah, this is a statement that was used probably at some point. This is a statement that is used probably at, because we have Uville, so this is a theorem, apply equal. This is this theorem that says that if you have a function that tends to 0 at infinity, then it is 0 everywhere. So we have applied this at some point. And I don't understand how that concludes the rest, but it's very strange. So that doesn't work. So let's quote this. So this shows that there are cases where it's very hard to understand what Mathlib is doing. But that's okay. So the point is that you see here we don't know exactly what Z is. So of course here it's a complex number. But the reason it knows that it's a complex number is that because here we have f with c of x, here I write c of 0, which so 0 is a complex number. So this is an equality of polynomials. And so the full sentence, Lin is capable to match the type of everything. But if you take a subset of the sentence, a lot of information is missing. And so it's hard to copy and to guess. And this is, well, okay, this is 1 over z. This is the fact that the inverse function is constant 0. I don't understand what they're doing. Maybe polynomial fun x, usually it should. Okay. So polynomial fun x, you say that, okay, to prove that a polynomial is constant, if you are over a domain which is infinite, then it suffices to prove that all values are constant.
And it's not true if you're not over an infinite.
Exactly, or over a domain. Over something where, for example, over an infinite ring where 4 equals 0, but 2 is non-zero, you have 2 times x, which is identically 0. So okay, so you apply this, and okay, so So okay, that's sure that sometimes it's difficult to read Mathlib, but you see how it is built. I mean, it's really built. They really try to prove general theorems and to apply them. Okay, so I think it's enough for today. We need rest.
No lectures tomorrow. You know it's a holiday.
Yeah, have fun.